Yes, thank you. Yeah, let's continue. So we had like this, the last, well, we know now what cat-zero cube complexes are and that they are useful. So yesterday we saw like this whole story of groups of birational transformations of surfaces operating on this blow-up complex. And now we would like to do something similar in higher dimensions. So the goal of today is to construct cat-zero cube complexes with isometric actions of Urech, but this time X is an arbitrary variety. And now if you want to do the same as we did in dimension 2 or something similar, you get into trouble. I mean, the first obvious problem is like we don't have strong factorization in dimension 3 or higher, or like, well, we don't know whether it exists or not, but I know it's a risky factorization. So if we have a birational map between, let's say, projective varieties, like we don't know whether we can always like blow up smooth subvarieties and like, yeah, get such a resolution. But even if it would exist, we would get in trouble to like would be hard to construct cat-zero cube complexes. Like the usual problem, like you have. If you want to blow up curves that intersect, right, then you blow up one curve, you blow up the other curve, and then you blow up the two curves again, and then you don't get isomorphic varieties. Then you would have to think, how do you do it if you blow up something that's a point on a curve for the curve, and then the point, it's like each of these issues, one has some ideas how one could fix it, but in the end, it never adds up. And also, I think it's always one cannot hope to have something similar in dimension 3 as we have in dimension 2, where our vertices correspond to projective varieties with vertex stabilizers that are automorphism groups. Because, for example, Charles mentioned these monomial transformations, and then in dimension 3, this group is GL3 Z, and we have seen this has property FW, so this one would have a fixed point. But then one can see that this group of monomial transformations cannot be conjugate to a subgroup of automorphisms. No, we don't know existence. Like not existence of by smooth centers that you blow up. That's still an open question. Smooth centers, yeah. It's open. Yes. Yeah. On the left side, right. Oh, just on one side, it's okay. Yeah. No, that we have like in dimension 2 or so. That's open. It's like my dream was for a while. Well, if one could assume it exists, and then one could show that this would lead to cat-zero cube complexes, and then one could derive a contradiction, that would be a very beautiful proof that it cannot exist. But yeah, so far the dream hasn't worked out. So just because it would be beautiful, maybe it's true, right? So we don't know. Anyway, so this doesn't work. But also, if it would work, it wouldn't help us. So what we do is we will just do something even more basic and banal than in dimension 2. So we use this factorization that also Evgeny already used in his course. So if we have a birational map between two varieties, and now we can really just use the definition, right, of birational transformation. So we know there exists like open-dense subset here and an open-dense subset here that are isomorphic. So in some ways we have a variety U and then we have an open embedding here and an open embedding here, two different ones. And this gives us a factorization of this birational map. And instead of blowing up points, what we do is basically we remove subvarieties until we fall onto U, and here we also remove subvarieties. So instead of blowing up points, what we do is we add or remove subvarieties. This doesn't exist. Yeah, exactly. So we use this instead of this. The idea. Okay, so let's make this a bit more precise. So basically what we want to do, we have to be a bit careful like with adding and removing subvarieties. So what we do is we just the first step, we only remove or add subvarieties of codimension 1. So maybe so maybe let's make just some terminology. So if we have x and y varieties, then we say that a birational map from x to y is an isomorphism in codimension L if the exceptional loci of f and of f inverse have codimension strictly larger than L. So we already saw before like a so-called pseudo isomorphism. This would just be an isomorphism in codimension 1. Okay, and then we can look at the group of pseudo isomorphisms, pseudo automorphisms of variety, or of automorphisms in codimension L. It's just we denote this by pseudo automorphisms, and then we put here the L. Good. Okay, so now for the construction, let's construct our cube complex now. Okay, we have x. Let's say, okay, in this like what you see here, like I mean, what we do here with this u, like directly see what we will lose is that our varieties are projective. So we have to work with non-complete varieties. So, but what we will still use is that they are normal. But okay, that's not a big restriction. And now we construct the following cube complex. So C0x. You see C0, so later on there will be other numbers here. You can already think about what cube complexes this can be during this construction. Okay, but what are the vertices of this cube complex? We look now again at equivalence classes of pairs. A pi, where A is a normal variety. And phi from A to X birational map. We look again at marked varieties. And what we say now is that two such marked pairs are equivalent. If this map, or the composition of this, like the difference between these markings, so phi inverse composed with phi going from A to B. So if this is not an isomorphism as we had in the blow-up complex, but here we ask that it is an isomorphism in codimension 1. So we just want that the exceptional locals of this map and also of the inverse don't have any, don't contain any hypersurfaces. Okay, and now the edges. Again, a similar story. So we put an edge between a vertex represented by A phi and a vertex represented by B psi. And we can even orient it again from A to B. If there exists a irreducible hypersurface, H in A, such that, well, the one down here is basically just given by removing H from A, and then the marking would then be phi restricted to A without H. And yeah, that's sufficient. And then for the n cubes, we proceed as before. So whenever we see the one skeleton of an n cube, we fill it in with an n cube. So here this means A1, phi 1, well, let's say maybe V1 to V2 to the n form n cube. So if there exists I such that write Vi as well Ai phi I and irreducible hypersurfaces H1 to Hn contained in Ai, such that all the other, so that the Vj's, they are just given by, well, removing some of these hypersurfaces from Ai. And then here, well, phi restricted to Ai without this whole thing for each j. Okay, so that's the definition. Let's maybe look at examples of how such edges can look like. So one example, okay, that's the easiest one. If we just take, for example, okay, let's still look at the surface case. If you take P2 identity, I mean, we can just connect this to when we remove the line at infinity. This is connected then to A2, and here, well, the identity restricted to A2, which is just the inclusion of A2 into P2 identity. But then we also have another example, like we can also blow up, right? Like if we have a if we blow up a smooth variety of codimension bigger than 2, Then, well, we get by the blow up, we get a new hypersurface in the y. So basically, then we have y pi is connected also with an edge to x identity. Yeah, because, well, if you remove the hypersurface here and here, we just have to remove something very small. That's like of big codimension. So if we remove the hyperplane here, then what remains is pseudo-isomorphic to x, because here, like from here to here, it's the inclusion, and the other way around, it's just kind of like the codimension bigger or equal to 2 variety that we have blown up, where it is. So in some ways, what we see if we have okay. So basically, the whole blow-up story is still in some ways present here. Is just kind of like that we add many more vertices and edges. So we can see, like, basically if we have work on a surface and we look at the blow-up complex, then we can see this as a subcomplex of this complex. But the embedding is not at all isometric. Let's write this as a remark. S is a regular projective surface. Then the blow-up complex over S is a subcomplex. Of C0 of S, but the embedding is not, or it's not an isometric embedding. So let's look at an example. Space. So for example, if we, okay, if you take, for example, automorphism of A2, and let's say, for example, something of very high degree or some kind of Henon map, degree, I don't know, bigger or equal to 2, I think that's sufficient. And then we have here a P2 identity, right? And now here we want to go to P2 F. So usually what we have to do is here we have to blow up many points, right? So let's usually can be very many if the degree is high, and then we have to blow them down again. So we get something here of length at least 6, right? If we have quadratic or, but so that's in the blow-up complex. But if we now look at this in our complex C0x, right, then we have a shortcut, like we can just go to A2 identity, which of course is the same as A2 F, because F is an automorphism of this one. And here is just one edge, and here we have just one edge, just distance 2. Okay. So in some ways, it's already displaced that we will lose lots of information by passing to this complex, just because we have many more vertices, and then like there's many more elements that have fixed points. This usually makes us lose information. But nevertheless, the advantage is it works for arbitrary x, and we can still, although it being so basic, we can still get some information out of it, out of the group structure. So okay, now we want to show that this complex is a cat zero. But actually, what we do will show something some ways stronger. So like, what we want to show is this cube complex essentially just consists of one single cube, so one large cube. Okay, it's like highly infinite dimensional, but what I claim is like if we take a finite set of vertices, then they are always contained in a cube. So that's the proposition I'd like to show today, theorem. So every finite set of vertices say A1 phi 1 up to AN phi n in our cube complex is contained in a cube. So you can think of it as like one giant cube, but of course like of uncountable dimension, right? So it's still a structure of cube complex, but yeah, if you take finitely many, they're always contained in the cube. Now, of course, a direct corollary of this theorem is that this implies that the cube complex is cat zero, right? It's simply connected. So if we have a path, again, it goes on the one skeleton, passes only through finitely many vertices. But if they are contained in a cube, of course, we can contract the path. And also all the links being flag is kind of like follows directly. Like if you have a point, you look at your you fix a vertex, you look at your link, so all the adjacent vertices, they are pairwise connected. I mean, okay, take any set, they are contained in a cube, so it's kind of like it's the simplicial complex you get is it's very easy. It's kind of like a complete simplicial complex, and all the simplices are filled in. Okay, a direct corollary of this theorem is that C0x is cat zero. Okay, but let's prove this theorem. So what we do here is, okay, so let me explain. So okay, we have here all the A1, A2, all the way to AN, and all these markings to X. And now what I claim is that, okay, we can find variety Y up here, and then birational maps to all our AI. Let's call them psi I. Such that, well, the whole thing commutes, and such that the exceptional loci of the inverse of this phi I, so phi I inverse, has codimension at least strictly bigger than 1, or 2 or larger. Okay, so it's a claim that such a Y exists, and we can just construct this. Well, okay, let's say for n equal 2, right? So we have just A1 and A2. And now, but we can look, okay, we can first take like a completion of A1 and A2. And such that it's normal. And then we look at the, I mean, here we have the maps by 1, by 2. So here we have the map by 1, phi 2 inverse phi 1. And now what we look is we can look at the graph of this map, of this birational map. So this we have already seen. So and then we take the normalization of the graph. So just take y to be normalization of the graph of phi 2 inverse opposed with phi 1. And here we have these, where we then have these morphisms down here. And now we already saw before, we can now apply Zariski's main theorem to see that kind of like the exceptional loci here of the inverse has to be of a codimension at least 2. Codimension is strictly bigger than 1. Okay, and then after, okay, so we can do it for 2, but then, of course, we can just continue. So if we have 1 here for 2, then we repeat the same for this new one and the next one until we get a y, this property. Yeah, then after induction. So we get such a variety y. Now, okay, and then of course after if we remove the completion from the A1 to AN, of course then we here have just the birational maps, so it's not morphisms anymore, but still like the exceptional loci of the inverse stay small. Okay, so then we have such a y. Okay, so we are in this situation now, and now, okay, now what we can do is now we can just shrink the AI. Like if we remove loci of codimension 2 or larger, this does not change our vertices. So we just change the representatives, and then yeah, we have that the inverses here are actually isomorphisms to the image. So so after shrinking AI, we may assume that psi I inverse gives isomorphism between AI and its inverse of the AI. So basically, we can see that AI psi I is now the same as psi I inverse of AI, and here we just take phi I composed with a psi I restricted to psi I inverse of AI. It's a bit of cumbersome index yeah, notation with all of this, but how it goes. Okay, so in some ways what we wanted is just like we can like embed all these AI into this Y. So we see them all as sub-varieties of the same Y, and there's a global like the map is given by the same map. So what we can do now, we can look at the union of all the AI in here and the intersection of all the AI, and this gives us these are the two that give us our cube. So Okay, so we just take A to be just the union of all these psi I inverse of the AIs, and B we define to be the intersection of all these AIs. And now we look at we glue now our maps together. So we want psi to be the birational map from A to X, such that the restriction of psi to each of these is just given by I composed with psi I. So we just glue these maps together to one map from A to X. Okay, and then if we take I don't know, H1 to HR, the irreducible components of A without B of codimension 1, of pure codimension 1, then we get exactly what we wanted. So let's write this down. Okay, so we have all these HI. So then we see that each of these AI by I is just given by taking A and removing some of these hypersurfaces, and then correspondingly restricting psi to A without these hypersurfaces. Again, just up to codimension 1 isomorphism. So this means that the AI by I are contained in the cube, in one cube. So in the cube that is defined by this vertex A psi and the irreducible hyperplanes, hypersurfaces. E1 to ER, H1 to HR. Okay, so this shows that our cube complex is cat zero, but at the same time it even describes the structure of this cube complex. Essentially, it's just like uncountable sequence of increasing cubes, or countable depending on our field, of course. Okay, so now we can define, of course, an action again of the group of birational transformations of X on this cube complex. So we define that BRX acts on isometries on this cube complex C0 of x just by acting on the marking. So we say again f, so the image of this vertex is again a f phi, so we just act on the marking. So this again gives us an action by isometries. And again, it preserves the orientation. Okay, so it's very similar to what we did before. Yeah, getting quite warm in here. To wake up, like what are the stabilizers of vertex in this case now? Third automorphisms of the corresponding were exactly so. So we have this similar observation again, f a phi. So this is equal to a phi. Well, if and only if the two are equivalent, which means that phi inverse f phi from A to A is an isomorphism in codimension 1. So what we get is that the stabilizers of vertices correspond to third automorphism groups. Yeah, so it's like the groups of pseudo-automorphisms of A, right? Like, and we say element is pseudo-regularizable if it is conjugate to some pseudo-automorphism. Yeah. Okay, and now we see like these groups can be very large and poorly understood, right? Okay, we like already for surfaces, for example, it could be A2 here, so we have all the automorphisms of A2, but then in higher dimensions, it can be something much worse in many ways, right? It can just be, maybe it's not affine even, it's just a quasi-projective or something with automorphism group that we don't understand, that the pseudo-automorphism group is maybe even more complicated. Yeah, I'm not making good advertisement for our cube complexes here. But okay, we can still like cat zero cube complexes. Okay, so now we know the stabilizers of vertices. And now next step we want to do is, again, as before, we want to understand distances and we want to understand what are the hyperplanes in our cube complex. So what are the hyperplanes? Again, if we have a vertex A phi, and we have again a hyperplane, like if we have H, then this gives us defines as a hyperplane. So basically H is given by a hypersurface, an irreducible hypersurface in A. And then we just remove this hypersurface. This gives us an edge. So this triplet A, phi, and H defines an edge. And hence a hyperplane in the cube complex. Here we have to be a bit careful, right? We have the hyperplanes in the cube complex, and we have the hypersurfaces on our varieties. Not mix them up. Okay, and now the question is again, when are two of these triplets, when do they define the same hyperplane in our cube complex? And we have very similar lemma to the one we proved in the case for blow-up complexes. So we say that, you can see that triplet A phi H, and another one B psi D define the same hypersurface, same hyperplane. If and only if D is not contained in the exceptional locus the exceptional locus of the map, the thing going from B to A, so that would be phi inverse psi, and H is the image, but here we have to be precise, so the strict transform so let's denote it by phi inverse psi of D. But yeah, it's the strict transform of D of D under phi inverse psi. While I clean the blackboard, you can quickly compare this to the lemma we had about the blow-up complex and hyperplanes. Okay, and I will not give the proof of this lemma just because it's the idea is very, very similar to the proof in the case of the blow-up complex. Just this time we go, like we just use again our factorization, right? Like we have A and B here, and then we look at the factorization, strong factorization that we have, and then again this gives us of the difference between the markings between the two varieties, and then we can see again, like, okay, if they are if they satisfy this, then they have to define the same hyperplane, just because we can again just in parallel transport the corresponding edge along this path, and the other way around, if we know that they define the same hyperplane, this means that the two corresponding vertices are on the same side of this hyperplane. We can find a geodesic that does never leave this hyperplane, and then we see that this has to be true. So yeah, that's the rough idea again. So I will not go into the technical details. Good, so okay, like that. Now, okay, let's make some notation. Okay, now we want to say what is the distance between two vertices. And this, again, we do similar as before. So what we did before, it was just like the number of base points of this map plus the number of base points of the inverse, and this gave us a geodesic. So this time it will basically just be the number of hypersurfaces that we remove here plus the number of hypersurfaces that we remove here. So for this, let's introduce the following notation. So we have the exceptional locus of F. And now if we put a 1 here, this is just kind of like this will denote the set of irreducible components of pure codimension 1 of the exceptional locus of F. So. And yeah, then we of course want to look at the number of elements of this. So number of such components. Okay, and now the lemma is again very similar, is that the distance between two vertices in our cube complex, this is just the number of exceptional reducible components of pure codimension 1 in the exceptional locus of phi inverse psi plus this number for psi inverse phi. And yeah, again, the proof is almost the same as for in the case of the blow-up complex. Again, we just look at this path. So by this factorization gives us a path between these two vertices, and here we just remove hypersurfaces. Here we add hypersurfaces, and that's exactly the amount of hypersurfaces that we remove, and this is the one that we add, or the other way around. And then with the lemma before, we see that this is actually a geodesic path. Good. Now we go through the whole list of what we did for the blow-up complex. So now we look at the types of isometries, right? Like we saw, there are either it preserves an orientation, so everything is good. So if we take f in B or X, it has to be either elliptic, right? So it has a fixed vertex. So yeah, this means that f is conjugate to some pseudo-automorphism of some variety, y. And the other option is that it is loxodromic. And now in this case, again, as we did for the blow-up complex, we take a vertex a phi that lies on the axis of f, or on a axis of f. And so, okay, we have again, as before, because it is on an axis, we know that the restriction to this axis is kind of like a really translation. So we have that the distance between a phi and a f phi, and then a f square phi. etc. That's always the same distance here. So we have that. So we have that number of exceptional divisors of, well, now we have to do it again as before. It's the same argument as in the case of base points. This is equal to n times the number of exceptional irreducible components of the exceptional divisor of phi inverse f phi. Right, it's again the same argument. We know the distance between this one and this one is this number plus the number of the inverse. And so we have this n times, but this is also at the same time cannot be any bigger than that. So we have to have that. We have this equality. Just, yeah. So for all n bigger than 0. So essentially, it's exactly, like literally the same arguments, just having number of irreducible components of codimension 1 of the exceptional divisor instead of base points. Okay, and now what we can do is, okay, last time, that's like the next dynamical invariant. So last time we defined the dynamical number of base points. So this time we can now define like the dynamical number of irreducible components of codimension 1 of the exceptional divisor. So let's maybe not write this out, but we just write this new 1 of f just to be the limit for n goes to infinity of these components, f iterated n times, divided by n. A priori, that's like an interesting question. Like you take a birational transformation, you iterate it, you see how does the exceptional locus change if you iterate it, like how many irreducible components of codimension 1 does it contain. And this cube complex is in some ways like made to answer this question, right? And it shows that it's actually either bounded or the growth has to be linear. Yep. Yes, yes. Yes. No, not exactly not that, because that was exactly if you take an automorphism of A2, right? You like you just have always you just contract one hyper surface, but the base points grow linearly just because like they're all piled up on each other, right? You have like a tower of base points, like they're all infinitely near to each other. And it's just one hyperplane, right? Like if you take an automorphism of A2, you take the line at infinity, you blow up a point on this line, and then you blow up again a point infinitely near, so you get like one of these zigzags, and then after you collapse the whole thing again. So you have more and more base points, but yes, exactly, yeah, it's much, yeah. Exactly, like you cannot have more, well, you cannot contract more curves than you have base points of the inverse. That's true, but the other way around is very well possible then. Okay, so let's write the theorem, which basically here we have the proof. So if we have an element f in Urech, then, well, we get that this dynamical number v1 is always an integer. And that actually there exists a variety y and y from x to y, a rational map such that the number of exceptional of components, exceptional locus of phi inverse f phi actually is exactly this dynamical number. So in particular, this one is 0 if and only if f is, well, conjugate to such a pseudo-automorphism. Okay, so also for this number of exceptional irreducible component of the exceptional locus, we have either it's bounded if and only if it's regularizable, and otherwise it's of linear growth with integer with the integer coefficient. About yeah. Here it's arbitrary dimension, yes. But also it's really like just the hyper surfaces contracted. Like it's not like what we had before. It's not with the base points. It's like that was. Again, like okay, we had like dynamical degree, like that was like a real nice dynamical invariant, and you had dynamical number of base points that was a bit more pedestrian maybe, and this one is even more pedestrian. But okay, it works for all varieties and all dimensions, so it's nice, and we know the growth is linear, and the question is fairly natural, so it's a good thing. And yeah, then again, we have, by applying the theorem of Gerasimov, we see that if we have a subgroup of Urech, then G is conjugate to, well, again, to a subgroup of pseudo-automorphisms. For some y, if and only if this number of exceptional irreducible components of the exceptional locus is uniformly bounded for all f. And this again, the same, really like literally the same argument again as with the base points. I mean, of course, if it is conjugate to such a subgroup, this has to be globally bounded. But also, if it's globally bounded, this means it operates on the cube complex with a bounded orbit, and this implies by the theorem of Gerasimov that it fixes a point, and if it fixes a point, it is conjugate to a subgroup of the pseudo-automorphisms of some variety y. And then there's another theorem that that we get for free. But here I would like, so okay, this theorem, it was proven by Serge Contat and Yves Cornelier. Like a couple of years before we did these cube complexes. And I have to say this paper was actually, okay, it's like the basic ideas behind this are very, very similar to this one. So they do it in the language of these pseudo actions of groups on certain sets. And this is kind of also related to Katsura cube complexes in some ways. And yeah, so they use this language and they proved this theorem with this. And also their paper was a heavy inspiration for constructing these cube complexes. So you should give them credit. But okay, in this context now we get it really like directly for free. So if we have a subgroup with property Fw, like that's what I introduced yesterday. So a subgroup with the property that if you have an action on a Katsura cube complexes, it always has to have a fixed point. Well, okay, if you have here a subgroup with property Fw, this means it has to have a fixed point and hence a fixed vertex. So it has to be pseudo-regularizable. Any x. If it, yeah, it has to be the same. I mean, if it's conjugate, it means it's conjugate by birational map, so it has to be the same dimension. Yeah, it's like birational equivalence. So being conjugate means there exists a birational map from x to y. Okay, and now the question, of course, then is if you see this theorem, and that's also what Serge and Yves asked, is like, okay, do we really need pseudo-automorphism here, or could we have like automorphism surface? And like the next step, it was being motivated by this question, but okay, it will give more. And then also Yves Cornelier actually showed it that you can do it for automorphisms exactly at the same time as we did, so it was in parallel. Okay, it was a bit different. He showed it for algebraically closed fields. On the other hand, he did not assume that y is separated, or that x needs to be separated. We do it for varieties, but for all fields, slight differences, but probably his proof could also be made for all fields. But what we do is actually, so the thing is now, like, okay, there was a reason why I said like pseudo-automorphisms in codimension 1, and then I said also we have it in codimension 2, 3, 4, etc., right, up to our dimension. And the thing is, why should we stop here and just take our variety and we remove and add hypersurfaces? Like, can't we just do the same? We take a variety and now we remove and add codimension 2 varieties. And this is the idea of the cube complexes. We call them CL of X. So again, we have to say what are vertices. So okay, it's very, very similar to what we did here. Just have to change the codimension. So it's again pairs the form A phi, where A is a variety, and phi is now a birational map from A to X, but it is a isomorphism in codimension L this time. And now we say that A phi is equivalent to B psi if psi inverse composed with phi that goes from A to B is not just an isomorphism in codimension L, but also even an isomorphism in codimension L plus 1. Okay, so these are our vertices. Okay, now the edges cube complex, like it will not be of any surprise. So it's exactly what you think. So we make an edge between the vertex represented by A psi and B phi, the orientation from A to B. Well, again, if there exists a near reducible subvariety, let's call it D in A, of a codimension, have to be careful, I think L plus 1, such that the restriction of, so that B psi is just the same as A, where we remove D, and here we take psi and we restrict it to A without D. And then, of course, the n cubes is as before, so I will not write this down now. Like just whenever we have a cube, we fill it. Good, so this gives us a new cube complexes. And now again, the claim is that these are cat 0. X are at 0. Okay, let's just give the idea of the proof, because I think we are all getting to the limit of our energy to concentrate, and probably time to sit somewhere in the shade. So the idea of the proof is basically, okay, to show that they are simply connected. It's again like the same proof as for, or the same idea of proof as for the blow-up complex. Just this time, so again, like if we have a path in the one skeleton passing through finitely many vertices, now what we do is we take now not something that dominates, but like something that's down here, so like the open that injects into all of them. And then with the same argument, you can show again that we can contract the path down here. Again, if we have something like that, where we remove one subvariety to get to this vertex and another subvariety to get to this vertex, we can just remove both of them to get down here, and then we can move the loop over this square to get down here. No, here it's not a giant. In general, it's not a giant cube anymore. Yeah, you can show like you can use, for example, you look at a flop and then you can see it's not. Yeah. So these are cube as cube complexes. They are more interesting probably. And then, well, okay, to see that the vertices are like all the links are flag. Well, it's also quite straightforward. Like if you can again look, if you have a vertex, then you look at the edges that descend. So there it's again similar, like if you can remove something here and remove something here, you know it's in a square, and something else here and here, you know it's in a square. You can also remove all the three and it's good. Or if the vertices go up, then so basically you can add a subvariety to one, like here, or we can add another subvariety, and then we can add a third subvariety. And now we know that pairwise they glue. So then we can just use apply the like standard gluing lemma from algebraic geometry, right? Like if you can pairwise glue all of them, then you can glue all of them together. So it's basically just you need some gluing lemma, and then follows that the links are flag. Okay, so they are cat 0. Now, of course, here we don't have an action of Urech anymore. But what we do have an action is of the group of pseudo-automorphisms of codimension L of X. So the group of pseudo-automorphisms of X in codimension L acts on this cube complex by isometries. Again, as always, just acting on the markings. Okay, so in some ways, yeah. So these cube complexes are good tools to study the group of pseudo-automorphisms codimension L of X. The question is, somebody wants to study them. That's, I think, a very good tool. And we will use them for something a bit different. But okay, still here, I want to remark, like everything that we did for C0 of X, we can do here again. So the stabilizers of vertices are correspond now to groups of pseudo-automorphisms, but this time in a codimension L+1 of A. And then again, we can define dynamical invariants for these maps, right? Like we can look the number of irreducible components of pure codimension L of these ones. So we can define a new L of F, again to be the limit of, well, number of exceptional of irreducible components of the exceptional divisor, this time of pure codimension L+1 of F to the n, be divided by n. So again, for elements F in this group of pseudo-automorphisms. Etc. And then we can rephrase our theorem. Okay, we don't have to write it again. Like we can just take this one and we just remove here. Okay, here instead of Brx, I mean Brx is just pseudo-automorphisms in codimension 0. So here we just make a automorphism in codimension L, and then here we put L. Did I do it correctly, or should it be L+1 there maybe? Yeah, I think it should be L plus 1, right? Yeah, because for 0 it's 1, yeah. So here we can replace it by L plus 1, and here we have it exceptional of L plus 1, and yeah. Here pseudo-automorphism is kind of like pseudo-automorphism with co-dimensioned L plus 1. Right, and then we have this same theorem here. Okay, but now what we also have here, if we have, well, and of course also this one, what we have here is that if we have a subgroup with property Fw, and here we take the group of pseudo-automorphisms in a codimension L, with property Fw, then G is conjugate to a subgroup of pseudo-automorphisms of codimension L plus 1 of some variety. And now maybe you already see the proof. Let's write this down. So if G in Urech has a property Fw, then well, we can conjugate there exists a phi from X to some birational map from X to some variety Y, such that phi inverse G phi is contained in the automorphism group of Y. And the proof is exactly, some of you thought. So we look at the action of G on the cube complex C0 of X. Now we know it has a fixed point, so we know it is conjugate to some pseudo-automorphism of some variety. So we know that G fixes a vertex. So this means phi inverse, okay, let's say phi 1 inverse G phi 1 is a subgroup of a pseudo-automorphism group in codimension 1 of some variety Y1 for some Y1. Okay, this means now the group acts on the next cube complex on like C1 of Y1. So we get an action on pseudo-automorphisms on C1 of Y1. And this has, because it has property Fw, it has again a fixed point. And now we continue like that, right? And then at some point we end up with automorphisms. Of Y, yeah. And then we have the theorem. Good. I have two other applications I wanted to mention, but I can just do this orally. So one of them is, okay, this, if we have an element that is not F in Urech, that is not conjugate to to a pseudo-automorphism, so it's not pseudo-regularizable, then we know the number of the irreducible components of codimension 1 in the exceptional divisor has to grow linearly. And then actually from this we can deduce that in this case, the degree growth of f, if we iterate it, has to be at least linearly. Whereas we know if you have a birational map, either it's pseudo-regularizable or the degree growth has to be at least linearly. It has to be at least linear. It's in general very difficult to say the degree growth of a map, and usually people expect, or I don't know, one could hope that if it's not bounded, that it has to be at least linear, but that's wide open. And yeah, so this is at least for one class of generic element, it has to be at least linear. On the other hand, I mean, generically, as Charles explained it anyway, it has to be exponential. And then the question is what happens in the pseudo-regularizable case. It's very difficult, right? But okay, here's one more class. And then the second application is one can look at if we have an element that's loxodromic, so again, like the thing grows linearly, like the number of irreducible components of the exceptional divisor. So you can look at the centralizer of such an element. And what you can show with this is basically this, either your f preserves, permutes the fibers of some rational dominant map. But if it does not do that, then actually the centralizer has to be small. So it has to be up to finite index f, like the subgroup generated by f times a torsion group. Now, usually we hope expect this torsion group to be finite, but so far we can only show it is f times a torsion group. But yeah, I think it's better to stop here and cool down after a bit. Thanks a lot. Oh, very good. Or maybe first, Mark, it's maybe safer.
So I just want to ask for the theorem, the y you get, what can you say about it? Can you assume at least quasi-projective or not even that? When you conjugate to an anthropomorphism group?
Yeah, I mean, okay. I mean, we can say that our varieties are all quasi-projective. There's no problem into it. Like if we start with a quasi-projective variety, and now we blow up, yeah, like,
Yes.
If we glue the things together. Okay, so in the first iteration, it's yes, by the construction we did with the graph and stuff. In general, the question is if you glue these together, could happen that you get something a priori, that you get something that's not quasi-projective. Yeah, okay, maybe you have to think about it.
Oh no, okay. Can we, as in the blow-up complex case, get the regularization, Veil's regularization theorem with a similar argument as, so going from C0 to C1?
Yes, so okay. So it works definitely if we take, like to get to a pseudo-regularizable. This works, right? If it's of bounded degree, it contracts only finitely many things. After one has to start thinking if there's an argument that if it's of bounded degree in pseudo-automorphisms of some variety, if this implies that it has only bounded many reducible components of codimension L+1, I would expect yes, but yeah, one has to be a bit careful because like it's really like the varieties we are working with are not complete anymore, right? Like you could just remove a point, and then if you iterate it, you get more and more points, right? But so, yeah, probably one would have to work a bit.
But I'm scared to throw it now. I think it.
No, it's
Wow, okay. Yeah, so these pseudo-automorphisms in codimension L, L+1, and so on give us a filtration. Does it make sense to look at successive quotients? Are they interesting?
so for a given variety, you mean? They are not normal, no.
Okay. Yeah.
Yeah, I think it's,
Okay.
yeah.
Yeah, then that's obsolete. Thanks.
And also, again, like, you have to keep in mind, it's not, often when one sees something like that, one thinks of a projective variety here, like smooth projective. Here it's like not complete, right? So you can have, already in surface case, you could end up, you can just take A2, you remove a point, and then already linear ones, right? They are just pseudo automorphisms.
No more questions?
I wonder if G is a subgroup of bounded degree, it is satisfy the property FW?
And no.
Okay.
No, I mean, you have many, right, like you can have a free subgroup of bounded degree or so.
Okay. So is this theory can prove that if G is a subgroup of the bounded degree, it has a V regularization?
Yeah, that was a question of Alfonso. So, yeah, I'm not sure. I mean, you can show that if it's bounded degree, then it's pseudo-regularizable. So this you can show, but that it is after it's regularizable, I think one has to work a bit, or it's not clear for me. But then how to go from being an isomorphism codimension 1 to being an isomorphism codimension 2 as well.
Okay.
It's not entirely clear.
Okay.
But especially we have Weyl regularization, so we know it's true already. But I don't know if one can find easy proof with that in some way.
Okay. I see.
Can I ask? I just wanted to ask one thing that I did not quite remember from the last lecture. So was it this Kazatan property T that is stronger than the property FW?
Yes, so everything with yes.
Oh, Kazatan property is stronger than the FW. So I think I heard this like somewhere, but mapping class groups can embed in the like a Cremona group of high degrees.
Yes.
Yeah.
But the thing is usually, I don't know, like also the braid group or stuff like that, yeah, so the question is, but the way usually these embeddings work go like through these character varieties. So usually what you do, you construct this embedding into the Cremona groups by constructing an embedding into the automorphism group of an affine variety first. And hence on this cube complex, you already know it has a fixed point, right? So it's always these kind of embeddings don't help us to get fixed point free actions of braid groups or mapping class groups on that zero cube complex.
Okay, thank you.